So where were we? We were looking at the issues with this first definition and seeing that we have a few limitations. So I'm giving you the definition. So this is what you see in textbooks, typical textbooks on databases. You basically have a few schema attributes that you defined outside of this relation thing. So you say, these are my attributes. Then you associate the attributes with domains. These are the sets in which the values can be, domain integrity. And then you say the tuples that are in your tables, this is basically a mathematical relation over the domains, and this is called the extension of the table. So you have the attributes, the domains, and then the extension. Okay? So that is the textbook database that you will see. Now, this definition enforces domain integrity by definition, because you define a Cartesian product over the domains, so it forces the values to be in the domain of their column. So that is enforced. How do you get atomic integrity? Just take atomic domains. Take domains that just contain attribute values, like strings, integers, and so on, but not tables. You cannot have a domain of tables, because then you would have a table in a table in the table, right? And relational integrity is also enforced by definition, because the relation gives you that. When you have a relation, you can't have any holes, right? Because the relation, the relation always gives you, the relation always gives you tuples with the same number of values. So you also have relational integrity. Okay, so that is what we get. Who agrees with this? Okay, very nice. Okay, so here's now my second attempt. So we are going to start with the attributes. These are the headers, the column headers of your tables. What are attributes? They are just strings, right? It's just a name. It's the name of your column. So it's a string. And so every attribute is an element of the set of strings. Okay? For the mathematicians who are bored, the set of strings is a monoid endowed with the concatenation operator, right? Just for the mathematicians. Okay. Now, these are examples of attributes. Technically, it can be any string, right? But in practice, first name, birth date, product ID, account ID would be, name would be attributes. Technically, also these, but I don't know if people would actually call their columns with actual values, right? So even though it's a load, I don't think these would be names, attribute headers. But we don't care. For the definition of attributes, any string will do as an attribute. So now, what is a record? Well, in definition number one, we said a record is a tuple. Well, in definition number two, I'm going to say a record is a map. A map from what to what? When you think you have a record in a table, what does it map to what? Well, it maps attributes to values. Who agrees with that? Okay, I have visuals, don't worry. So we need a set of values. These are all possible values you can have. Let's say, take atomic values just for simplicity and for the atomic integrity. And we need, let's take the set of all possible attributes, the set of all strings. So a record is a map from the set of strings to the set of values. Remember, a map is a partial function. So it means that it maps some strings, the attributes, to some values. And I have visuals, so normally I should have visuals coming right up. Yes, this is a visual. This is an example of map. It's a partial function, a map from some strings, 4 of them in that case. We map last, first, physicist, and year. These are my attributes, these are my column headers. And we map last to Einstein, we map first to Albert, we map physicist to true, and year to 1905, right? Do you agree? This is a map from strings to values. Who agrees? Who agrees this is one record? Who sees that this is a row in my table? Right? These would be my column names, and that would be the values that I have in my row. Very good. So again, remember, these are the maps that we saw right there, and this was actually another example just with a visual representation. That is the mathematical notation, and that would be the visual representation. Okay, so this is now the records. Not tuples, but maps. Now, who did take big data for engineers? None of you. All right, you're taking it in the right order then. Then you can take big data for engineer next semester. Well, the same thing here can also be expressed in a syntax. Does anybody know what syntax that is, out of curiosity? It's called JSON. Who heard of JSON? Right, that is the JSON syntax. So a JSON object technically is a map, right? And a JSON object can be a record in a table. And in fact, that's what we do in big data for engineers, right? So we can express the records as JSON objects. But anyway, for this lecture, we are not going to do this. That's for mathematicians. We are not going to do that. That's for big data for engineers. No, we are going to do this. This is our vision. The same thing. It's 3 times the same thing. This is the same thing as this. This is the same thing as this. But here I make explicit that the domain of my map, that's the strings. So I have here the attributes. These are the 4 attributes that are actually mapped to something, and the other attributes that aren't mapped, the other strings, I just leave them out. And then this is what it's mapped to. Last to Einstein, first to Albert, physics to Struve, and year to 1905. Who agrees that when I have a map, the order of the left values is irrelevant? Okay. So we fulfill our needs. We said we don't want the order of the columns to be important. That is the case right here. If in my map, I would just change the order in which I do that, mathematically, it's still the same map, right? Because again, visually, a map looks like this. So there is no real order between the rows, right? Okay, so that checks my boxes. This does exactly what I wanted to do. Here's another example where I have a map that maps 2 strings, university and city, 2 values. So university, ETH Zurich, city, Zurich. And again, instead of seeing this record as a tuple ETH Zurich, Zurich, that's what we did before with the first definition. Instead, we see it as a map that maps university to ETH Zurich and city to Zurich. Okay, who is with me? Okay, very good. Now, a map maps some strings to values, and we have a name for these some strings. We call it the support of the map, right? So when we have just the headers that are used in a map, we call it the support. Let's call it H. That's a subset of S. So we can also write support of T. So T is my record right here. That's my record. And the support of that record is the set of the attributes that are mapped somewhere, right? So this would be the support of it. Who is with me? Very good. Note that I called the support, the record that I call it T because it's commonly done because T is like tuple, but we just see it as a map. But you know, notations don't matter. We could call it F, A, X, alpha, beta, or whatever we want. It's still the same, right? But anyway, a record has a support that is the set of its attributes. Okay. Just need a sip of coffee. So now, since we saw that we can say that the records are maps, what is a table? Well, we can say a table is a set of maps. Who agrees? Okay, we can see a table as a set of maps, right? For example, below your eyes here are 3 maps. In front of your eyes, 3 different maps. And we can glue them together. Oh, sorry. We can glue them together like this, right? These 3 maps. Because here, I should not have put the sides in that order, but that doesn't matter. What is it doing? There you go. So here we have 3 maps that can be glued together as a table. Why can we glue them together as a table? Because they have the same support, right? They have exactly the same support 3 times. So this is a table. It fulfills what we call relational integrity when these maps have the same support. What is a counterexample of a set of maps where they don't have the same support? This is a counterexample. It's still a set of maps, right? We still have 3 maps, but these maps have different supports. So do you see now that if I don't restrict my set of maps, if I just say any set of maps, then maybe that's not a table, right? You agree this is not a table? Yes. So when I say it's a set of maps, technically I'm not calling just yet a table, I'm saying it's a collection, right? It's a collection, that's the very generic name in SQL and NoSQL system. It's a collection So a collection is a set of maps, can be this, can be that. But my collection, in order to qualify for me to call it a table, has to additionally fulfill one more criterion, that is relational integrity. I also ask that that collection, that set of maps, then all the maps must have the same support, the same attributes like this. And when I have a set of maps where they all have the same support, I can push a button and glue them together in this way, and now I have a table. Okay, so this is the idea. So with this second definition, I'm saying it's a set of maps, a table is a set of maps that also fulfills relational integrity. So a set of maps that have the same support. That's it. That's a table with my second definition. Okay. So that's relational integrity. How do I ensure atomic integrity? Well, I just need to take a set of values that only have atomic values. So that set V, that's the maps map to, that set V, I just take strings, integers, and so on, but there's no table in there. No recursivity, right? No recursion. Just sets of atomic values. Then I have atomic integrity. And the last one, domain integrity, I need to enforce it also additionally. So I need to say that my set of maps must also be such that everything that is mapped from last is always a string, first is always a string, there's always a Boolean, always an integer. More precisely, my set of maps must be such that for each column, I can find a domain that is consistent with that column. Right? In that case, I can. String, string, Boolean, integer solves that problem. Right? And then I can basically assign the domains. Okay, so I just formalized this better. I'm just saying that I must be able to find some domains. I call the domains that map the attributes to their domains D. So that for every, this is a scary math, right? So what do I say? For every record in my collection, for every map in my collection, and for every attributes that I have in my collection, then the value that the tuple associates with the attribute must be in the domain of the attributes, right? That's the domain. So they must be all in the same domain, all in the same domain, all in the same domain, right? So basically, I must have this T.A, that is the value right here. T is the tuple, A is the attributes. T.A belongs to my domain. And for all tuples means for every row, and for all attributes means for all attributes. So it means for every single cell in there, the value must belong to the domain. Who is with me? All right. So that's it. Okay, and that's a counterexample of domain integrity. Here I could try to say, okay, the first column is an integer, but that's not true here because that's not an integer. That's it. So that breaks domain integrity, right? But now something beautiful happens. Something beautiful happened because I'm now defining a collection as a set of maps, and separately from that, I can require relational integrity, atomic integrity, and domain integrity. It's completely orthogonal to my set of maps. So that's great because it's future-proof. Because it means now I can define sets of maps, the entire space, and I constrain it with this and with this and with this, and I get relational tables. Why is that great? Because then when we go to the more modern technologies that we have in big data and document stores and all these systems, all we need to do is drop these three restrictions, but we still have sets of maps. So this is what I mean with future-proof. In big data for engineers, it's also going to be sets of maps. It's just that we get rid of the restrictions. Who is still with me? Didn't lose anybody? Okay. But again, for this course, we are going to enforce most of the time these restrictions. So what did I just say? I'm saying a relational table is a collection, so a set of maps, that additionally fulfills my three constraints: relational integrity, domain integrity, atomic integrity. That is what we do in the beautiful world of relational databases. So I summarize, we have a set of maps, that's a collection, and if that collection fulfills my three criteria, then I call it a table. Plus, and that's the beauty of the system as well, how do I get duplicate records and how do I get an order in the record? Well, I just need to say, instead of saying sets of maps, I just say bag of map or list of map. So I could say a collection is a bag of map. That's if I want to allow records to repeat. That's a second taste. It's like vanilla, chocolate, and strawberry, right? So there's 3 different tastes. So we have the set of maps taste. We have the bag of maps that allows to repeat. So here I have twice the same map. And in that semantics, it's okay. That's a collection. How do I make it a table with bags of maps? Then again, same thing. I just say additionally, it fulfills my 3 criteria. Right. Then I call it a relational table. Strawberry flavor, list of maps. So now I say a collection is a list of maps. So now the order matters. There is a first map and a second map and a third map, right? So that's the list flavor. Don't be scared by the math. That's just a formal way of saying that. And if I want my collection, my list of maps to be a relational table, then again, I say it has to enforce these three criteria. So you see that we turn this into a Lego game because it's configurable. Just like you can pick between chocolate, vanilla, or strawberry, you basically can pick, do you want sets or bags or lists of maps? Fully orthogonal, you can make a choice, set, maps, list, depending on what you want. And then you can also say independently, do you want relational integrity? Yes, no. Do you want domain integrity? Yes, no. Do you want atomic integrity? Yes, no. We just decoupled everything. And if we do have all 3, then we call it a relational table. Okay? Sorry, not so fast, just before. Who is still with me? All right. So these 3 flavors of relational databases are very important. You have the people that like to use sets, you have the people that like to use maps, bags, and you have the people that like to use lists. And in practice, there's a bit of everything. So technically, if you look at PostgreSQL, PostgreSQL does support lists of maps, but you can also ask it to behave like sets, and you can also ask it to behave like bags, right? So it does a little bit of everything. So the systems that you have in practice, they do support bags and lists if you want duplicate records and if you want to have an order in the records. Okay. So we are making progress here. Now, so now we're slowly going to the practical side. So imagine I have my relational table. Doesn't matter if I took set, bag, or list, doesn't matter. But I do have, because it's called a relational table, my 3 criteria fulfilled. When that is the case, there is a new word that I'm introducing here is the word schema. The schema of a relational table. What is the schema of a relational table? Well, that's also called the metadata. The schema is made of a name for the table. We like to give them names, just like to pets. You give a name to your cats, and we also like to give names to relational tables. So this one we call scientists. And then in my schema, I have my names, the column names. So these are my supports. That is the same support for all records because we have relational integrity, PID, last, first, and country. And I also specify the domain because we have domain integrity. So it means that there is a domain for every attribute. So we say PID integer. Last, this is a string. First, this is a string. And country, this is a string. Plus, one thing that also belongs to the schema, but that we'll see in a couple of weeks. Do you notice the underline here? Right? I underlined these attributes. And indeed, I can underline 1 or more attributes if it's what's called a primary key. It means that it identifies a person. And here it means person ID, for example. In Switzerland, that could be AHV, AVS, right? So that's a social security number. And that uniquely identifies the records, and then we underline it to say this attribute is special because it identifies the record. Who is with me? Okay. And so in the next lesson, which I might actually be able to start today, we'll see the practical aspects of a schema because you can define your schema in SQL. You can literally write down your schema and create a table with that schema, and then you can put data in there. And so we'll see how we do this. So this is a schema. Now I have a few more slides, but it's just to annoy you with a bit more math, but also to say that nobody actually does that in databases. So if you are an absolute purist and you consider that my relational table is a set of maps, then this is how you would write it down. So this is my visual. And do you agree that this is how I would write it down as a set of maps? This is a set of maps. Who agrees? Okay, but you don't need to worry because nobody actually does that. That's not what people do. But mathematically, this is the underlying math. And this is what people work with in their Jupyter notebooks. But it's formally very precise. Okay. And now I actually did something without telling you, but nobody actually reacts this. If I go back a few slides here, I did something that I did not introduce. T.A. I did the T1, T2, T3 for the first definition, right? So the first value, the second value. But this was actually new. I did T.A. What is T.A? Well, that's T of A. If T is a function, a map, it maps an attribute to a value. So this is just a function call. It's T of A, but we don't write the function call notation. As computer scientists, we use a dot, a bit like in Java or C++ or Python when we access. Who uses Python? Who already used dict in Python? I should have told you a map is a dict. It's a Python dict. And so you agree that in Python, when you access a value associated with a key in a Python dict, you say .a, right? Or you can also use square brackets. It's just two things. So in object-oriented languages, we do that. So T.A. And so this is what I wanted to say explicitly on that slide, that I can write T.customer ID. So imagine this is T. T is this record right here. And if I say T.customer ID, then that's one, right? Imagine this is a Python dict, this thing as a map, then T.customer ID, and the other two. Another convention when you do it with LaTeX, because in LaTeX you can use things you cannot do in a programming language, you can use subscripts and fancy formulas, then it's customary in theoretical exercises to put it as a subscript, right? So T customer ID as a subscript. It really means the value associated with customer ID in the record T. Okay, who is with me? Right, very good. So a database is basically a set of relational tables. Now it's the Inception movie again, right? So a table is a set of maps or a list of maps or a bag of maps that fulfills my three criteria. And a whole database, when you create a database on your machine, it's made of plenty of relational tables. So now you know, when you connect to a website to order something online, there is a database in the background, and maybe there's 50 tables, 50 relational tables. There's a table of products, there's a table of customers, and so on and so on. That is a database, a relational database. Everybody with me? Yes? Let me still check. I think I need to get closer. Yeah, there you go. And I need to click here. So I really want to do this regularly. You know, it's a service lecture, so you're from many, many different departments of ETH, right? So I try to, make it in such a way that people are not too bored, but people are also still following, depending on their department. So on a regular basis, I'm going to do a poll like that. This is your remote control. You can slow me down, you can accelerate me, and then I can adjust my speed to you during the lecture. So now it looks good because most of you are following mostly, but not too much everything that I'm actually boring you. So this is looking good. Okay, so I try to do it at the end of every lecture to make sure that you're following. And again, if there's anything you don't understand, then send me an email, send an email to the TAs. Ask questions. You should really ask questions. Did we have questions on Zoom today? Not yet. You can really ask your questions on Zoom. Absolutely no problem, and I will answer them. I know that some people in the lecture hall, that happens a lot in my lectures, they also ask the questions on Zoom rather than raising their hands. That's totally fine. You can absolutely do this if that makes you more comfortable, right? Okay. So I'll get a sip of coffee, and then I'll then start already the next part then, because we are ahead of time, because you're such a great class.